Alright, today we get to learn about more derivative rules. And so today we're going to be working with exponentials and logs. All right, let's start with exponentials and let's try to get a little intuition about what the formula for the derivative of e to the x might look like. So over here I've drawn the graph of e to the x. And over here I'm just going to get a rough idea of what we think f prime of x is going to look like. So let's just start with this point at 0. What's the slope of f of x at 0? So if I draw a little sketch of what my tangent line might look like, I can see that it's positive, kind of low, so maybe we'd say it's 1 or something like that, right? So let's say it's 1, and so I'd have a point here for my derivative because my slope at 0 was 1. Alright, how about something just way out here? Let's get a little sketch of what my tangent line might be like. Look, it's really, really steep. All right, we don't really know what number it is. Let's say it's 10. It's nice up high, and when we're out here, so our slope is 10. So far we have 2 points for our derivative. Let's come over here, somewhere way over here. Let's kind of see what our slope is there. It's very, very shallow, right? So it's almost 0 probably, so something really low. So when we're really negative, it's a really low slope, really close to 0, but not exactly 0. Right? It's not exactly flat yet. So we can kind of see that actually if I kind of get an idea of what it might be like if I trace through these 3 points, I'm not doing a great job, but we see that the general picture is about the same, right? It's a little bit interesting, and that's actually true for e to the x. This is a very special function. It's how it's kind of why we have it almost, is that the derivative of e to the x is actually just e to the x. Right? If I have a form of something like a to the x, so a is a constant here, so maybe a is like 2, the derivative of this is going to be the ln of a times a to the x. Right? So just a very simple example, if I had something like d over dx of 2 to the x, this would be the ln of 2 times 2 to the x. So this one is not exactly the same, but it's a similar shape. If you take the derivative of e to the x, it actually is the exact same thing. So let's do an example down here where we talk about tangent lines, just so we can get a little intuition for what these formulas can kind of give us. So for the first problem, we want to find the slope of the tangent line to e to the x at x equals 2. So what do we do to find that out? Well, first thing is we'll do f prime of x is equal to what? And using our formula, we know that the derivative of e to the x is actually just e to the x. It's the same thing. So if I want to find the slope of the tangent line to e to the x at x equals 2, I'm just going to plug in 2 to my derivative. So f prime of 2 is equal to e squared. And so if you plug that into your calculator, you will get about 7.389. Okay, so a nice steep slope at x equals 2. How about if I wanted to find the slope of 3 to the x at x equals 2? Well, just like above, I'd have to take my derivative, and I wouldn't have f, I would have g prime of x is equal to, and I'd come up here and look at my formula, so instead of an a, I have a 3, and that number needs to be a constant there, and so I would write the ln of 3, I'm following what's over here, times 3 to the x. And so if I actually want to know what my slope is of 3 to the x at x equals 2, I'm going to plug in this 2 into my derivative. So g prime of 2 is equal to the ln of 3 times 3 squared, or the ln of 3 times 9, which if you plug that into your calculator, you will get about 9.8875. Okay? So just all we've done so far is some basic practice with these formulas, right? And they kind of work similarly to how they did before. So let's take a look at a more advanced example, and we're going to give you a slight extension to rule number 1. While the derivative of e to the x, if there's no k, is just e to the x, if you put a k up here with the x, so if you have something like d over dx of e to the 0.05 times x, you can follow this formula to get you the derivative. So you bring down your k, 0.05 times e, and then you leave the top the same. So 0.05 times x. Right? So with this formula and with the one before about a, we should be able to take these two derivatives, take the derivatives of these two formulas. So this formula, notice we're adding two things that we know how to take the derivative of, and so it's just going to be the sum of the derivatives. So the derivative of this from the power rule is I drop down my power, 2x, and then I do 2 minus 1 on top. Now the derivative of this, e to the x, is just e to the x. That's what my formula tells me. Or this formula will tell me that same thing if I set k equal to 1. Right? So the derivative of that is just e to the x. And so if I simplify, I'll get 2x plus e to the x is my derivative. How about this next one? This one's a little bit trickier. Now I have to follow this formula that I demonstrated here. Same idea, two things that I know how to take the derivative of. So it's going to be the sum of the derivatives. So I'll have 2e to the 2x following this one. And to take the derivative here, notice I have this constant out front. And so what do I do with that? And so remember from the last section, if I have a constant times something I know how to take the derivative of, so that thing I know how to take the derivative of is in the blue brackets right now, I can just do that constant times the derivative of what was inside the brackets. So the derivative of 4 to the x from my formula before is the ln of 4 times 4 to the x. So if I simplify this, I really can't do much, but I can remove the brackets. So this is plus 3 times the ln of 4 times 4 to the x. So, big idea from this first video, we really just learned two more formulas to get exact derivatives. We learned this one about d over dx of e to the kx. If we ever see something like this, we know this is the derivative. And we also learned a formula about a to the x. If we ever see a to the x, we know that this is the derivative.